mic on? Yeah, my mic should be on. What's up, guys? Kristen Ninja here, and welcome back to Study Sessions. Today we're going to be going over the basic concepts of electronics. Oh, well, I can hear myself. Okay, cool, great, awesome, amazing. So the basics of electronics. Um, oh, I can actually, since I'm not studying for an exam now, I can do this and check the chat. Well, no, I'm just gonna do it the way I normally do it anyway. Do it like this, put this here, and then I'll use my phone to check the chat. So if you have any questions throughout the stream, just just let me know, and I will. I already started. Go this way. Go this way. Goodness gracious, I'm over here at home. Can't even stream my own home. Was better off with the 3 bits per second Wi-Fi at A&M. Okay, anyway, and you're still audible. Anyway, um, so the basic concept of electronics. Um, well, there's one major principle that everyone who works on electricity or electronics who wants to do electrical engineering, any type of oh, hold up, let me change my thing real quick. I almost forgot I got to change my name. Forgot it was um anyway, the first thing you should know is Ohm's law. So we start Ohm's law by drawing a triangle. Actually, gonna use a fancy shape drawer thing. We're gonna draw a triangle here. That's gonna be our Ohm's law triangle. Then we're gonna draw a line here and a line here. So the first big thing that you should note with Ohm's law is that voltage, current, I'm going to draw these all in different colors so that way it's easy to see. Current and resistance. So all three of these together create what we know as electricity. Voltage is just a way of saying a potential difference. Um, that breaks down even further to be high, high minus low, high minus low. Now, high minus low is a really, really big simplification of the concept of voltage. Um, but that's because if you have, for example, the easy way to explain this is a bucket of water. So if we have a bucket of water, say, I said it a few weeks ago. I cannot draw right now. Let's see. Okay, let's say we have a bucket of water. And there's a small hole in the bucket. Well, we have a bucket of water and it's sitting on a shelf. And then below the shelf is an empty bucket. So there's a potential difference of the water here. So water high, and there's no water here. So this would be water low. Water low is typically referred to as ground. And ground is where all energy ceases. We have my granddad joining in on us today. Um, we're just going over some of the basic stuff. Um, it's gonna make more sense later. Hold on just a second.
Hey, Brenda, would you mind muting your mic?
I'm trying to find it. Oh, okay. Wait a minute.
Okay, cool. Also, you could turn your volume down as well. He and I happen to be in the same room today, so this is pretty neat, but also it's gonna make an echo. But anyway, so this is the basic concept of voltages how voltages are different between two different points. So um this is just like a rough example. So yeah, I guess that's an easy way to explain voltage. Current is a little bit different. Current and voltage is measured in volts if you didn't know. So now current is not measured in kerrs, it's measured in amperes. Don't ask me why the symbol for current is I and it's measured in amperes. Me personally, I would have said VAR, but look, man, I didn't invent this stuff. So you have to suffer through whatever Mr. Ampere decided he wanted to call this stuff because he's the one who discovered current. So with current, that is the flow of energy. Simply as like the rate of flow. So you have the rate of flow, which is what you can define as current. Um, with this definition of current, we could say that you could see the difference in current flows with like a stream. So this would be low current, or a river. This would be a high current. Then the beavers of our proverbial voltage or our proverbial Ohm's law ecosystem, where voltage would be like the water itself, current would be the river flowing. You have our beavers, which are the resistance. So you have resistance, and that's the opposition to flow. In other words, stops flows. And that's like if you were to have a dam built up in front of the river, so the water can't get through. So with all three of these things put together, I'm sure y'all are probably really well versed in this stuff already, but in case someone's starting, in case someone's like trying to watch the streams to learn a little bit more about electricity, I want to have at least like a basic principles one. So when you guys come back to um, your upper level classes, you have a little bit of a refresher in case you forget or something doesn't make sense at the time. Um, But yeah, so that's Ohm's law. So you can remember it at, so the way it's written is V equals I R, and that's the same thing as the triangle that we drew. You can see that. I will redo that real quick. These are one and the same. So let's do an example. We're going to do a voltage example first, and then we'll do like a how to solve for voltage, current, and resistance example. So our voltage example would be it's going to be really, really fast. If we have let's see, let's say we have a box sitting on top of a slope, and then after some time, the box is at the bottom of the slope. What is the difference? So let's say this is at height like 5 meters. This is at 0 meters. And this is just some length of this is all just some length. Doesn't really matter what it is. We can find the voltage between the 2 points because there's a potential difference of energy. So let's give the box a mass of like 10 grams. So we know from physics that force equals mass times acceleration. Acceleration is the derivative of velocity, so dv dt. I forgot what velocity for. I forgot what velocity equals. You can find velocity. Well, actually, no. We don't even need to find. We don't even need to find acceleration. Assume Earth's gravity. So let me write this legibly so y'all can actually come back and read this one day. So you know gravity is a force because you have to have a mass and an acceleration. That's what we get. That's what we call weight. So the mass is just how much matter is in an object, but the weight of an object is the force of gravity upon that object. So we'll have 9.8 meters per second. So that's meters per second squared. And then that is a mass of 10 grams. So we'll just say 10. That gives us a force of 98, I think it's newtons. And then because I don't feel like I don't remember um what newtons are in I don't remember what newtons are in joules. Any number from newtons to joules. Oh, cool. Amazing. So newtons is actually a 1-to-1 ratio to joules. So this is also equal to 98 joules of energy. So let me see, joules to volts. Voltage divided into energy by charge. Um, so 1 joule is 1 coulomb volt. So if we say J for joule equals C, V, C is coulombs, and V is volts. J is joules, and that's spelled Joules. Y'all can't see that because I'm not writing on the screen. There you go. Let's just say that the charge on the block, we'll just say that it's like, we'll just say like the block is just one proton. It's a 10 gram proton. So that would be a charge of 1. So we could say that the number of the number of volts, actually no. Let's say it's what's the weight of a proton? Let me find the charge of a proton. +1. Okay, and then weight proton 1.67. My calculator over here. Oh, yeah. Yeah, cool. So 1 proton has a weight of 1.67 times 10 to the minus 24 grams. So 1.67 times 10 to the minus 24 grams is the weight or mass of 1 proton. So if we have 10 grams worth of protons, it's a really positive block. This is a really positive block. Hope y'all get that joke. Yeah. So 1.67. So then to divide that, so this has a charge of 5.98 times 10 or 5.99. Because if you divide 10 grams by 1.67 times 10 to the minus 24, you get 5.988 times 10 to the 24th. That's how many protons would be in the block if it was a strictly positive block. That gives us our charge because each proton is worth 1 singular charge. So you would have 98 joules divided by this value. That equals your amount of volts. So if you have divided by that, you have a voltage of 1.63. We'll give it a 7. 1.637 times 10 to the negative 23 volts. That's a very, very small voltage for that amount of change, but that's essentially how voltages work because that's a potential difference. We gave it a charge. We have an amount of energy going into it. That's how voltages work. So now we can do an example of how to find voltage, current, and resistance. So granted, if you have any numbers you'd like to use, any favorite numbers or numbers you find interesting, you can just say, well, what do you want to solve for? What do you want to solve for? Voltage, resistance, or current? Okay, so if we're solving for current, we'll have I equals voltage over a resistance. So do you have any numbers that you like for any numbers that you particularly like? $250 for what? So we have 250 volts No, you're looking for resistance. I need a resistance value.
So
20 ohms resistance. So this is going to result in a very high current because current is voltage over the resistance. So if you do 250, I could do it by hand, but I don't feel like it. So I'm going to be lazy and use a calculator. Do 250 divided by 20 volts. That gives you 12.5 amps of current. By the way, just for a side note, this is the ohms. Ohms. Symbol. And that's what resistance is measured in. You're good. So you see ohms, that's what resistance is measured in. So if we have 12.5 amps, 12.5 amps is quite a lot of amps. Let me see. I'm gonna pull up like how, like, just to give you frame of reference. So we're just gonna go to OSHA.
if you were looking at voltage in the battery,
Mm-hmm.
you have high amps in the battery.
It depends.
You have 800 crank, 800 crank amps to start them in.
Well, that's a different type of that's a different concept. I'm talking more like how dangerous amperes are just by themselves. So you probably will need to use like there's going to be situations where you have a lot of high amp applications. Um, but just as a rule of thumb, any amount of current above 10 milliamps is capable of producing a painful and severe shock to people. Currents between 100 and 200 milliamps, or 0.1 to 0.2 amps, are lethal. Currents above 0.2 amps, while producing severe burns, unconsciousness, do not usually cause death if the victim is given immediate attention. Resuscitation consisting of artificial respiration will usually revive the victim. So you can be easily knocked out um, by amperes. Um, so you can see you can see the threshold of sensation at 1/1000th of an amp. You can see that a severe shock can occur. Severe shock or muscular paralysis can occur at a tenth of an amp, or I mean 100th of an amp. Between a tenth and 2/10 of an amp is death. You could have severe burns and stop breathing at an amp and above. Um, so low voltage, victims of high voltage shock usually respond to artificial respiration more rapidly than victims of low voltage shock. The reason may be maybe the merciful clamping of the heart, owing to the high current densities associated with high voltages. Uh, the resistance of the body changes depending upon the points of contact, the skin condition between the ears, Yeah, there's a lot of cool things you could do if you really want to do something cool to test your skin's resistance. Grab a multimeter, grab two ends of it, and put it at the highest setting for resistance, and you can measure the resistance of measure the resistance of your skin using a multimeter. Should be around like um 10 to 20 mega amp or 10 to 20 mega ohms. Um, Quite interesting. So while voltages can get very high, you might be wondering to yourself, how in the world am I going to touch anything above a 1 volt battery without dying? Your skin's resistance is pretty strong. Also, your skin is not conductive as a expression of how resistive it is. So you need something to create a current flow between the two ends of a battery terminal. That's why you also don't touch the two ends of a battery terminal with two pieces of metal, because you will shock yourself. It's not fun. Trust me on that. I've shocked myself before. It is not fun. Also, this is just like a politically correct thing. Um, if you didn't die, you were not electrocuted. You were just shocked. I know you feel like you died, but if you did not die, you were not electrocuted. You were shocked. So anybody you've gone yelling to them like, "Oh, I was electrocuted when I was a kid," guess you're talking to a ghost. Goodness gracious. Sometimes it bothers me. Sometimes it does bother me. But I try not to let it happen because not everybody understands. And I'm just an engineer. I just work with electricity all the time. It's just something that I do on a day-to-day basis. So it bothers me more than it bothers somebody else. I digress. So let's do a fun problem. So let's say I have like a bolt. Let's say that I have a bolt of lightning. So we get a cloud to ground lightning strike. So we get a big cloud to ground lightning strike. Um, no, let me pick a nice bright yellow. We get a nice cloud to ground lightning strike, and we'll say that clocked in at let's say we just had like our little guy Thomas Jefferson, he over here flying his kite, got his got his kite up there. Oh no, he's struck by lightning. You got the lightning running down the thing, and he's shocked. Oh no, what a tragedy. But let's say he was able to measure that, and he was clocking that at like, let's just say 452 million volts or 452 megavolts. And let's say his skin's resistance is 20 mega ohms. So how much current was in that bolt of lightning that he received in that short span of time that he was struck? Well, we can figure that out with Ohm's law, just like we did on the last problem. So we got 52 times 10 to the 6. Then you do 20 times 10 to the 6. And then you divide that by the other one. And that gives you, he got about 22.6 amps of current from that cloud to ground lightning strike. Now, we don't know exactly how much it was. We don't know how little it was. It's not that big of a deal. He survived, supposedly. I mean, he's dead now, so he supposedly survived. Um, but yeah, so that's how.
was that, pipe or the string a conductor of current?
Unlikely, but because of how strong the voltage is, with at a certain level of voltage, you'll have a breakdown current of a material. When it breaks down, it allows current to flow through it. It's the same concept of what happens with diodes, which is actually a good segue into what we're doing into the next section of electrical components. So now that you have like a basic understanding of what electricity is and kind of how it works a little bit, we have electrical components. So electrical components, we have our passive ones, which are resistors, capacitors, and inductors. We have active. There's a lot more active than passive, but the passive ones make up the active ones. So we have operational amplifiers. We have we have rectifiers. We have transformers. We have transistors. We have diodes. That's all the ones I can think of for now that are active.
So
In what way?
if you didn't have one, could you replace it?
Well, that would be getting into like our next lesson. We're going into like the stuff we learned in 355. If you go back to any of the other streams where we were talking about like how you can create any reactance with a short or an open wire given a certain length for a matched line, um, that's where that kind of falls into place. But typically, you can't really replace the active components because they have different purposes for uh, they have specific purposes. So these are also typically called op amps. Um, these amplify signals. These smooth signals. These change voltages or currents. These these are like switches. So switch circuits on. And diodes prevent two-way current flow. Resistors resist current. Capacitors build and store charges. Inductors build and store current. Now, I'm not the greatest physics person on the planet, so I'm not going to try and teach y'all physics. If you want to learn physics, go to a physics teacher, go to a physics professor, because I'm not going to teach you physics. I can't teach it that well. I can teach you electricity, but I can't teach you physics. Well, I could try to teach you physics, but I don't think it would end very well for anybody watching the stream. Um, anyway, so with these electrical components, just to show you a circuit with like all of them in it, you might have like a resistor, and a capacitor, and this is connected to ground. This is going into an inductor. This is going into a diode. These are both connected to an alternating signal, just for sake of ease. This is going into an operational amplifier. Up here, you might have a filter, so you might have like a low pass filter. Um, and then you'll have like a rectifier, like a half wave rectifier or something like that. So that would be like that. And that's drawn kind of like this. Um, what else? Then you might have a transistor connected here to control some light. So you have like a transistor. Um, yeah, so this over here is like a circuit with everything in it. This doesn't necessarily mean anything, but you'll probably see something similar to this at some point in your life if you ever go into the world of electrical engineering. You'll see all of this at some point. They may not all be on the same circuit, but you'll definitely see all of it at some point. Um, let's see. So the easiest way to teach resistors, well, the easiest way to teach this is do the passive components first. Maybe if I do another, if y'all are really down for this and do, like for summer school or something like that, um, I'll do like a lesson a week or something like that with I guess winter school. I'll do a lesson a week with electrical components and stuff like that until we get through all of them. But the easiest way to do this is start with resistors. So if we have like a battery, let's say 5 volts, and we have some resistor, and we have that's like 10 ohms. We have another resistor, and that's 35 ohms. So resistors in series, if you notice this is a series circuit, resistors in series, they add like you would add two problems, like you would add like basic addition. So this is equivalent to the circuit here, where you'd have a 45 ohm resistor. And then to find the current going through this entire line, you do 5 divided by 45, and that gives you 1/9. So your current equals 1/9 amp. I think that's like 0.188, something like that. I think that's what uh I think that's um the current flow through that. Um
Your current is representing, resistor one, resistor two. Resistor one, uh, your current is identified as the, what, the voltage divided by, resistor one and resistor two,
Correct.
that came out to be, 45. And, it come out to be, 45, that divided by
5 divided by 45, that gives you
45 divided by 5 or
5 divided by 45.
and they gave you,
That's equal to 1/9. I think that's 0.188. 0.188. I think that's right. Oh no, it's not. It's 0.11. My bad. Probably not. I mean, it's still it's very much in the danger zone, but it's so it wouldn't really matter. Um, the next thing that you should know is parallel circuits. So if you do a parallel circuit where you have resistor here, say that's 10 ohms, a resistor here, that's 10 ohms, and you have a resistor here, that's 20 ohms. Still say we have 5 volts. All of these can't add up like they do when they're in series. So you might ask yourself, how do we find the total resistance? Because we can find current is equal to the voltage total divided by the resistance total. And that gives you the total current. Now you can find the current going through each line, but I'll explain that a little bit later if I feel like it. But the way you need to do this is the total resistance of a parallel circuit. So the total resistance in the parallel circuit is oh, welcome to the stream. Thanks for being here. Oh, my bad. I'm sorry. I'm sorry. I'm sorry I wasn't reading the comments. Um, to answer Crimson Matrix, it lowers the amperage of the output. What exactly are you asking? It lowers the amperage of the output. The resistance, like resistors lower the current of the output. I think that's what you're asking. And if you're asking that, then yes. Um, but to keep going until I can like see what you're trying to say. By the way, thank you for promoting the stream. Shout out to yes, you're correct about the resistors. Shout out to Crimson Matrix. Appreciate you. Appreciate everybody in the stream. So our total of the parallel circuit is equal to 1 over R1 plus 1 over R2 dot to however many resistors you have. So since and also this is just a little trick of the trade. If you have the same how does it work? How does it work? I think it's like if you have the same values for all of them, so like if you have like 10, 10, and 10, and the same voltage, doesn't really matter what the voltage is. I believe you can do this as like 1 over the number, like the number of resistors that are the same times that resistance, and then you end up having like 1 over, no. I'm gonna just do it the long way and it'll work itself out. I'm gonna do it the long way, it'll work itself out, and you'll see what I'm talking about. So ignore this right now. Ignore this right now. We're just gonna erase that. Doesn't exist. So for this part, you would do 1 over 10 this is the easiest way to do it. So 1 over 10 plus 1 over 10 plus 1 over 20, and that equals 1 over RT. So if we do that, 0.1 plus 0.1 plus 1 over 20, that equals 1/4 equals, well, let me get this exactly. 0.25, goodness gracious. 0.25 0.25 equals 1 over RT. If you multiply by RT and then, if basically if you do some algebra, this is like a miniature algebra lesson. You multiply by RT on both sides, you get 0.25 RT equals 1. Then you divide by 0.25, divide by 0.25, and then RT equals 4. Because if you do 1 over 0.25, you get 4. So that would be a total of 4 ohms. And this is an important note to make, that if you want, I would recommend writing this down. This is an important note. In parallel, the resistance is always, I mean always, like the sky is blue, always like water is always going to be hydrogen and oxygen, always as in space is going to be cold relative to the temperature of the earth, always like your mom's going to be mad at you for having one sock on the floor, always. It's always going to happen. The resistance is always lower than the smallest resistor. This is an important note to make. So you might want to write this down if you're going into electrical anything, if you're going into anything like with electrophysics, electromagnetism, anything that has to do with this, that you have to deal with resistors. Even mechanical engineers and stuff, y'all have to deal with resistors and stuff like that. Like you might have to make some type of mechanical component resist the flow of water or something like that. So this is a very, 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 very important concept to know. Um, that I felt that you should know now. Anyway, so with 4 ohms of resistance total, we do 5 volts divided by 4 ohms, and that gives us 1.25 amps. Yes. Um, so that's how we solve that one. I think the resistor rule, there's a resistor rule that's like, um, let me see if it works before I like try to explain it to y'all. I had 1 over 10 plus 1 over 10 plus 1 over 10, 3 over 10, 3. No, that's not it. Um, let me see if I can look this up, because I know there's a almost like a cheat code. Um, ah, I knew it was something like that. So if you have resistors of the same, let's see, 0.1 divided by if you have resistors of the same value, so like in if you have two resistors of the same value, like if you had a circuit like this, we had 20 and 20, let's say 5 volts. Then you had like 10 and 10. You could combine these two resistors here to because the current would split evenly between the two. So you would really end up having like a 5-volt battery, and you'd have one resistor with 10 ohms and another one with 10 ohms and 10 ohms, you could also simplify down to 5 ohms. So I'm just going to simplify it down to 5 ohms. And then you would end up just needing to do 1 over 10 plus 1 over 5, which equals 0.3, 0.3. 1 divided by that, that's 3.333 repeating. And that's how many ohms are in this circuit. That's the same thing as if you had 3 10-ohm resistors in series with each other. So you can so if they have all the same value, I think you're safe to add them all up. So if you had like 1 over 20 plus 1 over 20 plus 1 over 20 plus 1 over 20, and you had let's just say you have 4 over 20, and you're trying to get that to be trying to find the voltage there. You gotta wait 2 hours for your lobby to be done. I mean that's not fun. At least you have something to study, or at least you have something to do while you wait. See 4 over 20, that equals 0.2. Do 1 over that. That gives you 5 ohms. If you do it this way, the 1 over 20 plus 120 plus 1 over 20 plus 1 over 20. And then you divide that, or you divide 1 by that, it gets the same answer. So that's how it works. If they're the same value, you can just add them together, and then divide by that, that total value you get, but they must be the same value resistor. So let's work an example problem. Shout out Dr. Fink. Appreciate you teaching me all this stuff about static DC circuits. So let's do an example. Let's say we have 8.3 volts. We have see one. Also, the way you could denote a parallel circuit from a series circuit, if the two ends of a component, like here, well, actually, let me do it on a different part. Like here and here are connected to both terminal ends of the battery. That's how you can tell if it's a parallel or series circuit. That's an easy way to tell. Anyway, so let's just say this is 76 ohms. This is 50 ohms. This is 10 ohms. This is 30 ohms. Goodness gracious, I need to write this neater. And then this is 40 ohms. So we want to find I total. So Granddad, do you have any idea how to find I total?
Find out, told you. You compute the value of your resistors and then multiply those times your, you multiply that time.
We have a voltage though. We're looking for the current.
Okay, but then voltage and you divide it by resistance and you get your current.
So you're basically saying we need to do VT over RT, right? So how do we find RT? So I'll explain it in just a second, but there was a question in the chat. What if you have two resistors that are about 5.5 and three resistors that are about 10, all in a parallel circuit, like one resistor? Oh, okay. Oh, I just went over that. So if you look back here, I did something similar. Let me write it a little bit neater so you can read it a little bit better. Um, so you have 20, 20, 10, and 10. So with this 20, 20, 10, and 10, the two that are all the ones that are the same, they can add together, but the ones that are not the same cannot. So the reason that I was able to break this down even further is because you have a 10, a 20 and 20 that breaks down to 10 ohms of resistance, and the 10 and 10 they break down to 5 ohms of resistance. Then I end up just having a 10 and a 5, and then I just do the 1/10 plus the 1/5, that gives you 0.3, and that gives you 3.3 ohms over each other. Um, that's an easy way to explain that. Um, that can also go into this next problem that I did right here. Um, so this example problem that I've done here, if you have 10 ohms and 30 ohms in one column, and 40 ohms in another one, you have 76 ohms and 50 ohms. So oh my goodness, there's so many resistors. I have no idea what to do, but trust me, I'm an engineer. We got this. So the first thing that you can do is if you notice you have a series circuit. Let me do this in a different color because you know I love my colors. You know I love colors. Shout out Corey Kenshin. Switch the colors. If you notice here, this is a series. This is a series circuit. So we have we can do 10 plus 30. So that gives us a new equivalent circuit of 8.3 volts, 76 ohms. 10 plus 30 is 40 volts or 40 ohms. 10 plus 30 is 40. So when you have 40 ohms, there's another 40 ohms here. And then 50 ohms down here at the bottom. If you haven't been able to tell, 76 is my favorite number. So now we have 240 ohms. Wow. Well, would you look at that? That just breaks down to 20 and 20. How crazy is that? Or not 20 and 20, it just breaks down to 20. So that equivalent circuit, let me point it out here. These two are in parallel, they're the same. That equivalent circuit becomes 8.3 volts, 76, 20, 50. So now we just add all these together because now this is just a series circuit. So 76 plus 20 is 96 plus 50 is 146. 146 ohms total. Then we can just do VT over RT. That equals 8.3 volts over 146 ohms That gives you roughly 55, wait, no, 56.8 milliamps. Any questions on how I got there? I'll give it just a minute for the chat to catch up to the rest of the stream. I don't see any questions in the chat. I think I might do one more example and then I'll call it for the night. Because I am in break mode. This is just more for instructionary purposes. Look, man, I explained this how I had to learn this. So funny story. It's not really a funny story, but it's funny in hindsight. I failed my first two exams going over this stuff, so I got really good at doing it. So I passed the class. Yeah, it was not a laughing matter when I got my grades back, but still pulled it out. Oh man. Um, okay, so the next example will be still in DC circuits, but I'm going to teach y'all. I'm going to draw this out. I'm going to give you like a minute to see if you can solve it, and then I'm going to show you how much you overthought the problem because it really simplifies down to a lot less than that. So let's see, 10 volts. Yeah, this should. Yeah, yeah, yeah. Uh-huh. Yep. Okay, so this is the problem. Let's see. This is a problem that you could solve. Um, I'm gonna give y'all a minute to solve this. You have 1 minute. You might be asking yourself now, he was doing so well explaining how to do everything just a moment ago. What is going on in this problem? How could he be so mean? He only gave us a minute to solve this? My mom's gonna think I'm a failure because I don't know how to do this at all. But don't worry, Chris the Ninja's got you covered. So this is 2 lessons in one. This is teaching you to pay attention to what you're doing. In a DC circuit, so this is a DC circuit, you'll notice because of a battery. This is a battery. If you see a battery like this, it's a DC circuit. In DC circuits, I didn't tell y'all this for a reason because I wanted to teach you this quickly. In DC circuits, capacitors act like an open circuit. Inductors act like I don't know what that says. I appreciate it. I appreciate it. Inductors act like a short circuit. That being said, well, this inductor, that's just a short. This capacitor, this is an open circuit now. That means that this is broken. This is an open circuit. That means this is broken. So wait a minute. Hold up a second. Hold up just a second. If this is broken here, let me circle this. If this is broken here, doesn't that mean this whole rest of the circuit can't activate? Which means if I were to ask you to find the current, there would be no current because the circuit's broken. There's nothing completing the circuit. It's one of the tricks that my professor in my third semester of college, no, my fourth semester of college taught me. Or he played on us. He drew all these components we were panicking, and he just canceled one thing out and it blew the whole circuit out of the water. And we were all shocked and surprised and like, what in the world is going on here? And I never forgot that lesson. And I don't want y'all to ever forget that lesson because it's very important to pay attention to what you're writing on, pay attention to what the question is being asked, and pay attention to how the question is being asked. If you notice, I didn't even give you anything to solve for because I knew you wouldn't be able to solve it because there's nothing to solve for. Now, let's do a no, a capacitor acts like an open. So capacitors act like an open circuit in a DC configuration. Um, I'll do a switch problem in the next. I'll do switches and stuff in the next study session because it'll make more sense after this. Because I have to go over like charging state and other stuff like that. Hold on just a second, y'all. Um, so the last problem of the night. This is going to be the last problem either way, but the last problem of the night. Let's do a circuit. Let's say 15 volts battery. We have a 5 kilo ohm resistor. We have a short circuit can actually be intentional. So don't get in the habit of thinking a short circuit is accidental every single time. Sometimes it can be sometimes it can be intentional. Have a capacitor here. Let's see. That there. Have inductor here, so that's like 5 millihenry. We'll have a resistor 20 ohms, and we'll complete the circuit. So if we're asked to find the total current here, this circuit, with what I just taught y'all, well, if there's a oh, that should not be Henry, that should be farads. From what I just taught y'all, if this is an open, this whole branch does not exist. So this gets erased. And now this being a short, that just turns to a short circuit. So now you just have 5 kilo ohms plus 20 ohms. That equals 5,020 ohms. Then you do 15 divided by 5,020. That gives you 2.99 milliamps. And that's how you solve that problem. If you missed it, rewind the stream, go back like 30 seconds, show you exactly what I did. But that's going to be the last one for today. Maybe I'll do these once a week or something like that. Once we get, I'm definitely coming back when school starts back up. I'm doing all my homework on live stream. I'm live streaming all my homework. Because that's going to help me pass my classes. It's not for y'all, it's for me. But with that being said, I want to say thank you guys so much for watching this video on the stream. If you liked it, give the like button a nice slap to the face. Like and subscribe today to join the Shinobi Force. And I'll see all you guys. 4 to 5 fast cars on the wall next time.